Okay, now recording. Will we ever see any more of the UGA topology talks on YouTube? Oh.
Very soon.
Okay.
All right, there we go.
Oh, Piedmont Athens Regional. Yeah, I like that.
Well, you know, I do feel very grateful. So to both.
I'm grateful to them for some things too. They've had a big facelift since you were there. Lots of.
What's that?
They've had a big facelift since you were there. Lots of construction, and it's a,
Oh, okay. Yeah. No, I
better as hospitals tend to go.
Yeah. Anyway, well, you tell me when I should start. And should I go an hour, 50 minutes? What's your standard?
I think like most of us kind of have something to do around 4 o'clock. So,
Okay.
if it spills over a little bit, but I think it's nice. I mean, I usually tell people if we derail you with lots and lots of questions, then it's fair for you to go take a full hour to talk because we didn't give you a chance to say stuff. And maybe give us 10 minutes for questions. Does that make sense?
Okay, that sounds fine. Sorry.
All right. Well, looks like we have a good virtual and in-person audience. So it's thanks a lot, Danny, for being able to reschedule at the last minute. And it's a pleasure to have Danny Ruberman, who's going to tell us about diffeomorphism groups and embedding spaces for format.
Okay, well, first off, thanks very much for the invitation. Thanks. Actually, when Dave says thanks for being flexible, sorry, what he's not taking into account was that I actually had totally lost track of the date. So when he wrote to say, hey, could we delay a couple of days, it was just fine by me. So anyway, that worked out well. I'm sure I would have been ready, but I just somehow hadn't turned the page on the calendar or something. Anyway, this is work. I think I've talked about it. I think I talked about it last year at the Georgia Topology Conference. So I tried to put a different spin on things. I kind of looked at my notes. I said, well, that was a pretty good talk. Maybe I should just give it again. But then I thought, oh, that would be kind of cheesy. So this is a joint project. The current work is all joint with Dave Auckly. And the theme is, which we may get to see a bit of, is the interaction between diffeomorphisms of 4 manifolds and surfaces, and actually surfaces, and I should also say, and 3 manifolds, although we won't see too much of that embedded in some 4 manifold. So let me start with a little prelude from the fantastic work of Simon Donaldson, starting in the, I don't know, 84, 85, that this started to become public, was examples of homeomorphic but non-diffeomorphic smooth manifold. So he did this using Yang-Mills gauge theory, which is also going to be our going to be the tool of choice for this talk, although other kinds of gauge theory should show up someday. And let me give you a concrete example, and I'm going to actually use this concrete example as the basis for a bunch of constructions as we go along. So suppose in CP3 you take a complex hypersurface of degree. You could do this any degree, and similar things I think are true. But let's say, for concreteness, take the hypersurface of degree 4. So there's a nice homogeneous degree 4 equation where the solution set, you can check the gradient's non-zero. So the solution set is a smooth 4 manifold. And so that's a complex surface, and we're not particularly concerned with its complex structure, but it also has other names. Some people would call it a K3 surface because it's an example of a K3 surface, meaning its canonical class is trivial, or actually some version of variation of this manifold is fibered, except for some singular fibers by tori, so it's called an elliptic surface, and in fact it's the elliptic surface E2. So it's in that guise that we'll kind of mainly use it. It's just somehow it seemed easier to say describe it as a hypersurface, but it's essentially fibered by tori. Okay, so and that manifold is interesting, but here's a slight variation, and I'm going to sort of tweak these kinds of do these sort of variations as we go along. Take some manifold X. Okay, so X is sort of mostly a fixed manifold for the duration. So take this K3 surface or degree 4 hypersurface and blow it up once. So that's an operation in algebraic geometry, which comes down to taking the connect sum with CP2, but connected sum is an operation in the world of oriented manifold. So I mean a particular orientation, not the complex orientation on CP2. So that's indicated by CP2 bar. So that might be called a blown up K3 surface or a blown up elliptic surface, or however you like. So here's an amazing fact that Donaldson proved, that manifold, it's easy to determine its homotopy type. In fact, it's homotopy equivalent to the connected sum of 3 copies of CP2 and 20 copies of CP2 bar. So its signature as it stands is, what is that, -17. They're homotopy equivalent, but they're not diffeomorphic. So that's an amazing fact. And Donaldson proved that by the use of what we now call the Donaldson invariants. As I'll describe it today, these are just going to be numbers, but in fact, they really have a more complicated structure, which is interesting and relevant for this whole discussion, but not the focus for us today. So we'll just think of these numbers dx as integers. So I will later on, as we go by, we'll wave our hands in passing at a very brief definition of these numbers. So in fact, the dy, in fact, in this case, that's equal to 0, and the point is this is not equal to 0. So what I'm suppressing is that this also depends on the choice of a vector bundle on X, and I'm not telling you what that bundle is. And again, that's an interesting and important aspect of the whole discussion. On the other hand, Friedman had shown it follows from, I don't know that he thought about the specific manifold, but he gave a classification of smooth 4 manifolds up to homeomorphism, and just from the homotopy equivalence, it follows that these in fact are homeomorphic. So these days we would say that they're exotic. It's an exotic pair, so it doesn't sort of say that one's normal and the other's exotic. They're just relative to each other. They're exotic. So homeomorphic, but not diffeomorphic. So and there'll be a few other things that are, sorry, they're going to have to flip things around here just notice that my iPad or remember that my iPad is not going to make it through the lecture. Okay, so made it through there. Okay, so on the other hand, going back to the sort of really early history of 4 manifolds, this is amazing theorem of Wall, maybe not so hard to prove by today's standards, that says that in fact, take that X and Y, and in fact, we could do this with any homotopy equivalent simply connected 4 manifolds, the same thing would be true. Then for some K, which which Wall doesn't tell us how to find, so some K, X and Y become diffeomorphic after you connect some with, well, he said S2 cross S2, and that's sort of good enough for us. Okay, so you don't know what K is. it's an interesting question for any given pair to find the minimal K. And as far as anybody knows, in any example, the answer is only one copy. So for this particular pair, the X and Y that we've got, so the blown up K3 surface and this connected sum of CP2s and CP2 bars, in fact, you could just take K equal 1. In other words, if you just add one copy of S2 cross S2 to both of those manifolds, they started off different and they become diffeomorphic. They started off homeomorphic, and whatever it was that distinguished them just disappears. So that's amazing. There's a whole series of results by Mandelbaum and Moishazan starting in the kind of late 70s and going through the early 80s. I think there's an excellent article in one of the Georgia topology conference proceedings that sort of explains, that kind of gives a good survey of this whole thing. So they proved this for lots of complex surfaces using sort of topological understanding of the way complex surfaces look. And in fact, go ahead.
When you say topological understanding, were they doing Kirby calculus or were they?
No, well, it's actually, it's kind of interesting. Moishazan sort of started this off, and Moishazan used ideas about Lefschetz pencils and so on. And he analyzed the sort of monodromy, and he said, well, okay, if you add something like CP2 or S2 cross S2, that you get a new kind of vibration. And he just sort of saw how various things kind of became undone. I will have to confess, I don't understand. I mean, I can't understand what Moishazan did at the time. He wrote, there's a long volume in the lecture notes in mathematics that explains this, and it's all about braid monodromy and stuff like that. So those of you who do, I see a couple of faces out there who I think are much more expert at this than me. You might find it interesting to go back and look at those papers of Moishazan. They're very hard. It's rather out. So there's a sort of geometric idea, and then there's a whole bunch of algebra related to computations in the braid group. So that's what Moishazan did. And then Mandelbaum actually reinterpreted it. I think Mandelbaum was his student. And I think I also may have misspelled his name slightly, but he reinterpreted that much more geometrically. So the only one of those results that I really understand is if you take an elliptic surface and you add S2 cross S2 to that, then they call this phenomenon almost complete decomposability. In other words, where you add something like CP2, and then the whole thing decomposes completely into pieces like this. And they showed that, for instance, elliptic surfaces have properties like that. And that's a very geometric argument. If you're curious, it would take a few minutes to explain it, but that's actually a five-dimensional handle argument. So with that hint, you might actually be able to somehow you do surgery along a torus and just sort of see what happens. So it's a really very beautiful argument I think that argument's probably due to Mandelbaum that kind of redid all the Moishazan stuff. Anyway, it's really great. It's a beautiful piece of mathematics. I think it's one of those things that everybody knows the statement of, but not that many people know the proof, but the proof's very nice. Okay, so there's sort of two kinds of stabilization, and we'll sort of, I think it's the second one that plays the bigger role for us. In other words, you could actually stabilize with CP2. And now here, it's important, now we're talking about, again, the orientations the orientation's really important. Let me just point out, but by another theorem of Donaldson from the same era, X connects, so the Donaldson invariant of X connects some CP2 bar is not equal to the Donaldson invariant of, excuse me, that should be a Y, connects some CP2 bar. So the sign really matters a lot when you're doing this stabilization. And somehow S2 cross S2, or if you like the twisted S2 bundle over S2, that's got both a positive and a negative. So that sort of takes care of everything at the same time. Okay, so and I should point out that yet another. I mean, it's a pretty good couple of years for Donaldson. This is all consistent with Donaldson's, the other maybe harder part of Donaldson's connected sum theorem that says that that if you add a CP2 or an S2 cross S2 to any old manifold, that more or less kills any kind of gauge theory invariant. Okay, so here's the first little moral or interesting thing that we're going to sort of take advantage of. So so stated as philosophy first, and the philosophy is, if you keep track of extra data about a manifold. Sorry, let me just introduce this notation. So X connects some CP2 and Y connects some CP2 are the same thing. Let's call whatever they are equal to, let's call it Z. And the point is Z has in it, most of X, and it has in it most of Y, but somehow they're all mixed up in some kind of way. But if you keep track of certain submanifolds of Z, then you can actually remember X and Y. So it's more data. So this part's actually pretty easy to, and I think was understood, I don't know, a long time ago. So one is that actually, let me back this up. So of course, CP2 has inside of it a two sphere, just CP1 itself, which is a sphere of self-intersection 1. And the boundary of the tubular neighborhood, therefore, is a three sphere. That's a familiar picture of CP2. So, but I have sort of two versions of X connects some CP2. So in other words, I have two CP2s in there. And viewed as X connects some CP2, I can think of this Z as giving rise to a sphere, which I'll label SX. And viewed as Y connects some CP2, I get a sphere SY. And those are both sort of sitting in the corresponding CP2 summands. And you can arrange, there's a little extra appeal to Wall's old work. You can arrange that, in fact, those are homotopic. But they can't be related by a diffeomorphism because you can recover X or Y from SX and SY. In other words, you just remove a neighborhood of SX and glue in a four ball, and you remove a neighborhood of SY and glue in a four ball, and you get Y. Okay, and here's a little point, which is an important bit of really three-dimensional topology, which is any diffeomorphism of S3 extends over the four ball. So it doesn't actually matter how, so you don't really, there's no parametrization involved. Like if you're going to cut something out and glue something back in, there's essentially only one way to glue that back in. So I won't have time to explain it, I think, if I'm going to let you all go on to your next things. But we're going to do something similar, or at the end, I'm going to, again, sort of wave my hands at some similar ideas where we do this with families of manifolds. And in that setting, it's also a hard theorem, but maybe even harder theorem of Hatcher's solving the Smale conjecture that says that even if you had sort of a family of spheres, maybe moving around in some fashion, parameterized by more or less anything, there's a consistent way to glue in four balls. So what that really says that this process of taking X connects some CP2 and essentially replacing it by X, by removing a neighborhood of that two sphere and gluing in a ball, that's called blowing down. So the other was blowing up. Now here I would get in trouble. I don't know if anybody's at heart in algebraic geometry. Blowing up usually means connect some with CP2. Sorry, CP2 bar. Thank you. But here we're doing the sort of what Dave always says, anti-holomorphic blow up. But I think that's such a mouthful that I just call it blow up anyway. Okay, so this is sort of, so maybe I'll call this going this direction, or I'll use Dave's phrase, anti-holomorphic blow down. And I think my H looks like a K, so I'm pretending to be, well, anyway. Okay, so in particular, that says that there's no diffeomorphism from Sx to S of Z that takes Sx to Sy. Friedman says that, in fact, there's a homeomorphism. That's not hard to deduce from Friedman's work. But in fact, actually, if we've started out by arranging them to be homotopic, then in fact, not only is there diffeomorphism, there's an isotopy or a one parameter family of homeomorphisms, starting with the identity that moves Sx to Sy. Okay, so in that sense, those spheres remember X and Y, and also by the same argument, I'm not sure why I gave them names because I'm not going to refer to them too much, but the boundary of those tubular neighborhoods, those three spheres also remember the manifold X and Y. So they're sort of an exotic pair also. So Sx and Sy are an exotic pair of two spheres. The boundary of their neighborhoods are sort of an exotic pair of three spheres. Okay, so maybe another way of phrasing this would be, from all that is that the space of embeddings in a given homotopy class of either, is non-zero, and moreover, it's mapped to the space of embeddings sort of in the topological category. That map's not injective. So in fact, okay, and likewise for embeddings in a given homotopy class of the three sphere. Okay, so in other words, pi zero just, it's not, in this case, not a group, it's simply a set, and we're kind of picking out a distinguished element. And so anyways, it's not, but you can still talk about whether it's injective or not. Okay, so that's sort of submanifolds, but so what I want to describe now is a way to pass from knowing something about submanifolds to knowing something about diffeomorphisms. And then as we go along, we'll see we can kind of cycle this around and say something more about submanifolds from knowing a little bit more about diffeomorphisms. But anyway, it's this sort of constant back and forth between mainly the surfaces and the diffeomorphisms. Okay, so here's how we do this. So it's just another bit of fooling around with CP2. So remember, CP2 supports a nice involution, which just given by complex conjugation, and because we're in real dimension 4, complex dimension 2, this is orientation preserving. So it's an orientation preserving diffeomorphism. In fact, as I've written it, an involution, which I'll just call rho for reflection from CP2 to CP2. And also notice it takes, if you take sort of the obvious CP1 sitting in there, or make, if you like, that's preserved, in fact, but that one also gets complex conjugated, so that's orientation reversing, so that acts as -1 on the homology of H2 because it takes that class to minus itself. Okay, well, that rho is very nice as an involution, but I kind of want to go all topological on it and just do a little isotopy. Since it's orientation preserving, I can just assume it fixes a point, and in fact, I can assume it's the identity on a ball. So I'm really thinking of it. So thinking of CP2 as sort of CP1, or a little tubular neighborhood of CP1, and a ball. It's the support. In other words, the part where it's not equal to the identity is just in a neighborhood of that CP1. And by the way, of course, that description didn't have anything to do with the orientation itself of CP2. So you could also get a rho on that CP2 bar. Okay, so maybe just flip that around. If I have any manifold Z with a sphere of, well, it doesn't really matter at this point, self-intersection +1 or -1, then you could write it as something connects some CP2, something connects some CP2 bar. This X is, not the special X. This is just any old manifold. And so I get a diffeomorphism from the manifold that had the sphere in it, which again, I'll call rho. And the way I want to think of it is simply as being, sorry, with respect to this decomposition, it's the identity on the X part, and it's the reflection on the CP2 or CP2 bar part. Okay, so that's why I made it. That's why I took rho and did it a little isotopy that made it be the identity on a ball. Okay, so that's that. So I'm going to write things of this sort, a bunch of times. So the sum of two diffeomorphisms, maybe along a sphere or along something, means you make them be the identity or make them agree near wherever you're summing, and then just glue them together in the obvious way. So the point I want to make is that that the diffeomorphism depends on the decomposition you've chosen, and that depends on the sphere. Okay, so spheres. So if I have an interesting pair of spheres, I might get different diffeomorphisms, and that's in fact was an idea that I had a long time ago, and after some years of struggle with this, finally proved in, so it was, I guess, a while ago, 1998. So in that situation above, this diffeomorphism up to isotopy, well, I don't know that it actually remembers what X is in the same sense that the sphere itself remembers X, but the isotopy class of that, or something about this, well, we can recover the Donaldson invariant of X. So let me, that's morally true, but let me try to be a little more precise about what I actually proved, and also stated in a way that's useful for talking about the results with that Dave and I have, the recent results. So instead of taking some four manifold connect some S2, I'm going to add a little bit more. So I think I wrote this below, but let me add not just CP2, but a couple of copies of CP2 bar. So essentially, because of that observation of Donaldson, that adding CP2s doesn't affect the Donaldson invariants, this doesn't affect things too much. It's just rather useful for the calculation and for the examples. So so I could have at the beginning started with instead of adding CP2s, I could have added CP2s and CP2 bars, but it just, that's not what Moishazan and Mandelbaum did. So anyway, I left it. In any case, so this is manifold M, and that's always going to mean CP2. Oh, so that has a, sorry, I was rethinking the notation, but didn't write everything back in. So that has a two sphere. I called it S before, but I'll call it H just to match so I can write the formulas the way I remember them. H, again, the same CP1. H is for hyperplane, I guess. And then in CP2 bar, well, there's also the same CP1s, but those in algebraic geometry are called exceptional curves. So I'll just call them E1 and E2. And I just point out again, for future reference, that this M, it's an entertaining exercise to prove that M, which I'm giving you as a sum of CP2 and CP2 bars, is the same thing as taking S2 cross S2 and adding one CP2 bar. Okay, so what do we do with all that? So I'm going to make a slightly more complicated diffeomorphism of that manifold M, and it's just a composition of two reflections. So one is something that's sort of just off in a corner. It's the reflection in, say, E2 or E1. It doesn't really matter. And the other is the reflection in the sum of these three things. So notice that H plus, if I take either of those classes, H plus E1 plus E2, its self-intersection, well, that's a 1 and 2 minus 1, so that's minus 1. And likewise, E1 and got self-intersection minus 1. So I do have those two reflections. Now, this diffeomorphism is interesting. It's not, in contrast to the reflections, which are of order 2 in homology or order 2 up to homotopy, in fact, even order 2 up to isotopy, these ones are, this composition is of infinite order. So you can just compute a matrix for what it does on homology. So it's a sort of more complicated diffeomorphism, and that's sort of for technical reasons that's important. Okay, so so what I showed a while ago, and I will very briefly define it in a bit or at the end of the talk. So I cooked up a gauge theory invariant. It was kind of I think after the fact, I realized that Donaldson had suggested something similar, but didn't have an example or didn't have a way to calculate it. In any case, there's an invariant, which again, I just call DZ of a diffeomorphism. And it has the property that if I take a four manifold X, I add on this M, right? So just again, just sort of somehow the picture, right? I have X, I stick on this standard piece M, I do the, here was X, I do the identity on this part, I do this diffeomorphism F, that remember, so remember, at this point, we may have, by adding M, because we added a CP2 or we added an S2 cross S2, whichever stabilization you want to use, we've sort of lost track of what the manifold is, because we could have started with different X's or an X and a Y and gotten the same manifold. But the diffeomorphism depends on those spheres, and you can sort of see it in this formula. So my invariant of this of the diffeomorphism is just the invariant of the original four manifold, well, with a factor of 2. Okay, so in fact it's an annoying that factor of 2 is slightly annoying, but it's there. In fact, I didn't write that. Again, that was a suggestion of Dave's to slightly modify. I had a slightly different construction, and the version I had a 4, which was more annoying than the 2. So the 2 is slightly less annoying. Anyway, so yeah.
Does this invariant, really depend upon Z being of the form we've been discussing, or it's just this result?
Yeah. So there's a little bit. You have to. So what is it? Again, I'm sort of suppressing things like what bundle we're on and various hypotheses about B2 plus of the various manifolds. So suppose maybe I should. I don't think I'm going to want to write this down, but suppose I have a manifold X that has the property that it has a Donaldson invariant defined on it. Okay. Maybe one of these numerical ones just to keep life simple. Then there's a bundle on that manifold connect sum M, and such that that supports this diffeomorphism, and then it has this property. So whatever the invariant of X, whatever the Donaldson invariant of X is, the Donaldson invariant of the corresponding diffeomorphism is, well, it's just that multiplied by 2. Was that what you were asking?
Yeah, that's great. Thanks.
Yeah. So in particular, I mean, if you take an X and a Y that have different Donaldson invariants, like the pair that I specified earlier, the Donaldson, you can arrange it so that the Donaldson invariant of X is, I forget, -1 or something like that, and the Donaldson invariant of Y is 0. So they have different. And this maybe I should write down. And maybe I should have made this point, but part of the theory is that isotopic diffeomorphisms give the same invariant. So that's sort of part of the theory, part of what I proved in that paper. So in particular, if you take the X and Y, so what X was some blown up K3 surface, Y was the sort of decomposable manifold to which it's homotopy equivalent. One of them has a non-zero invariant, the other has a 0 invariant. So then these two things are not isotopic, but again, the work of Quinn and Perron from the mid 80s shows that in fact those are smoothly isotopic. So what does that say? So this is supposed to remind you of the formulation. Maybe if I can scroll back without everybody getting seasick, it's supposed to remind you of this thing, that some map on homotopy groups is non-injective. Where did it go? So that says that the map on pi0 of diffeomorphism groups is not injective. Now, in contrast to the thing about embeddings, where the pi0, of course, is just a set, pi0 of a topological group is a group. So this is a group homomorphism, and you can talk about its kernel. And so I just did this with a specific manifold Z, but if you like, if you work at it a little bit, you can choose a manifold ZR that so that kernel here, which now makes sense because we're talking about groups, contains a free abelian subgroup of arbitrary rank or arbitrary finite rank. I guess a good conjecture or problem that that Dave and I have been thinking about for a while is, or maybe conjecture / question, can you take R? Can you find something of infinite rank? So I found something of infinite rank in in pi 0 of a subgroup of diff Z, but that doesn't actually do the job because, as you probably know, that a finitely generated group might have infinitely generated subgroups like free groups and stuff have properties like that. So okay, so that would be a really nice thing. I feel like that's possible, but I actually don't know how to do it. Okay, so that's all. Well, I don't want to say ancient history because then I'll feel bad, but that's from the past. So what have we done lately, I guess, is the real question. Well, the main point is, and this was a point that I thought about a long time ago, I just didn't know how to, and I thought of an approach, which is sort of what we'll see as we go along. But the main point is that, you know, these embedding spaces or the diffeomorphism groups, well, those, you know, they're not just discrete spaces. They have topology, and so maybe we can say something about their higher homotopy groups or their homology groups or you know, various other things that are associated to these. So, and that's what I want to at least state and very briefly sketch. So here's sort of the here's I always like the word omnibus. So it's partly because it means, you know, like supposed to cover everything, but it also refers to buses, which I was still find very puzzling. Anyway, so here's a sort of a theorem that kind of states a lot of our results all in one. It doesn't get everything, but you know, it's good enough. It certainly gets a lot. So suppose I take a K. So that's supposed to be like a dimension, and an R, that's supposed to be like a rank. So then we can find simply connected manifolds, Z, K, R. So the Z I showed you before, that's sort of the first of the lot. And embeddings, so you can find a two-sphere in this and a three-sphere. The three-sphere is really just the boundary of the tubular neighborhood of the two-sphere. And the following groups all have rank R subgroups. So the same. So that's where the R is in the subgroup. So we could get pi k of the diffeomorphism group. So I put here, by the way, I put a 0 superscript. Just it only really matters. Well, it matters sort of here. But anyway, so we're just going to look at a certain path component. So we're going to sort of fix the ice. So, but that's fine because when you look at the homotopy groups, you have to pick a base point. Okay, so pi k. So all these groups have z to the r summand. So pi k of the diffeomorphism group, the homology group in the same in dimension k. If you take the classifying space for diff 0. And as I say, that's sort of where the taking the 0 matters. If you look at the space of embeddings of the two-sphere, the homology of the space of embeddings, so this is all in a fixed isotopy class, or the homotopy groups of fixed embeddings of the three-sphere. All those things have large z to the r subgroups. Okay, so that's our theorem. So I don't know. I think last year when I talked about this, I wasn't so sure about the homology results. So that part's certainly this part. Well, this part's new. This part's new. I mean, and although I think these were sort of always there, those are sort of new. Yeah, and I'm not sure how that T wandered out of place. Okay. maybe I'll just pause for a breath and let you ask a question if you want.
I assume are these two spheres all square plus or minus one?
Yeah, I should say, actually, that's an excellent point. Let me just mention the name of Dave's student, Josh Druin, does this for spheres with S dot S. I don't know whether he does spheres of self-intersection 0. Well, let's just say not equal to plus or minus 1. I think he does S. He kind of builds it, yeah, for other spheres, and in fact, actually, and also for instead of for some lens spaces L of the form LP1 instead of S3. So, sorry?
Just because that's the boundary of the neighborhood of the sphere.
Yeah. So whatever, this P is the self-intersection. Yeah. So he's a PhD student. I think that's basically going to be his thesis. I think he's supposed to finish next year. So anyway, so that's sort of adapting the techniques here. So good question, but Dave already thought of it and he gave it to his student for a thesis project. So, and which he seems to have carried out. Okay, yeah, I'm glad you asked that because I did want to mention Josh's name and work there. Okay, so let me just throw in a couple of additions to this. I think, actually, I said this first one just because I didn't have a chance to look at the paper. But in fact, these Z to the R subgroups, you can take them. It's not clear that the subgroups anyway, you could take them as summands. Okay, so that's interesting. So I guess people, when they study like the kernel of knot concordance to topological knot concordance, you're sort of more happy if you can prove that there's something or other has a summand instead of a subgroup. So we get summands too. So that's how we're all up with the modern trends here. All of the constructed elements, the diffeomorphisms, the embeddings, all those things, those families become trivial in the topological category. And so here, actually, this constructed elements, let me just be careful in the subgroup. So this isn't necessarily true in the summand because we have to mess around a little bit. Those all become trivial after you do a single stabilization. So if you add S2 cross S2, the whole homotopy class or homology class, the whole thing collapses. It's really and that just seems like, oh well, that's kind of cool, but as an addendum, but that actually is sort of the whole point in some sense. And again, this was something we were looking for. We sort of had this idea in mind from anyway a long time ago. I think Dave seems to think we talked about this in 1998. I don't remember, but I certainly within some year, it's early the 2000s is kind of what I recall. But anyways, we had this idea for a long time. It took us a while to get it sorted out. Okay, so let me try to explain at least the beginning of this. It's an inductive construction. The induction is based on the construction of the diffeomorphism F that I described before. So I'm going to not review it, but let me just kind of make the notation a little bit elaborate. Actually, let me just say one last point. That's related. It's sort of related to both the stabilization and this thing about the trivialization in the topological category. So there's this theorem about in the topological category that homotopy of homeomorphisms implies isotopy in the topological setting is a really hard theorem. I don't know if anybody's ever tried to read that paper of Quinn's or Perron's paper. They're hard. They're really hard, and to me somewhat mysterious. And and certainly nobody knows anything serious that I know. Actually, I don't know anything at all about like taking a loop of homeomorphisms. I don't know a criterion that would say a loop of homeomorphisms is contractible. In other words, bounds a disk of homeomorphisms. So all of the topological isotopies that go into the statement about the things becoming trivial in the topological category, they all just come back to the same. They all are built out of the same topological isotopy of just a single diffeomorphism. So that's part of the package. Again, if somebody really wants to roll up their sleeves and think hard about handle body theory and all that stuff, then I suppose maybe there's some theorem to be had in the world of, in understanding pi1 of the homeomorphism group. I don't even know where to begin with that. That's a hard subject, but an interesting one. Okay, so let me sort of go through the construction, or a bit of the construction. So remember what the setting was. So I'm going to just introduce some notation. I don't really know why I decided to put in the notation other than to sort of say, here we have a 0, 1, and I'm going to go show you how to, the 1 was the rank, and I'm going to leave that alone. Okay, so I'm not going to show you how to raise the rank. That's just sort of like, if you know some gauge theory, it's sort of obvious what to do. So what I'll show you is how to raise the dimension. So this is the, let me just write that. That's the K, and that's the R. So I'll show you how to raise the K, at least at the beginning. Okay, so here's the setup. This is the exact same setup as before, just with a couple of subscripts. So I have X. I have some diffeomorphism from X connect some that manifold M to Y connect some that manifold M. And as I pointed out, we could do this just with the CP2. So I could assume that the diffeomorphism actually takes the CP2 bars one to the other. Okay, so it really doesn't matter. Okay, so and I have the sphere SX, which was this one, the sphere SY, which was this one, and those are, as I said, pointed out, those are not isotopic, not even connected by a diffeomorphism. But what a theorem that Dave and I and Hee-Jung Kim and Paul Melvin showed, I don't even remember, 2015, I just as an approximate date, we went looking for this theorem for this exact purpose. It says that, in fact, those two spheres are isotopic, smoothly isotopic. So let me just emphasize that. Smoothly isotopic if you stabilize once more. So this is kind of like the Mandelbaum-Boishauzon thing, that all you do is stabilize once and things become trivial. It's actually a more direct argument than that. It uses a nice picture of, you can sort of visualize those spheres inside those complicated, at least the manifold X. It's pretty easy to sort of find those spheres. Okay, so they become so again, it's not hard to prove, using Wall's results, that spheres that are homotopic with maybe some hypotheses, like the fundamental group of their complements are trivial with like these spheres. Those spheres are isotopic if you add enough S2 cross S2s, but the point is here you just add one. So, and we've showed, and this is part of a general phenomenon. It's not completely general. It's not always the case, as some recent results using fancier gauge theory show. So but in particular, it follows that if you take the interesting diffeomorphisms, the identity of X connects some F, the identity of Y connects some F, and you just stick on the identity on this manifold M, then those become isotopic. Okay, so so maybe I should have introduced this before. Let me sort of measure the difference between these two things, and by just calling it alpha 0. So that's an element. Well, so I take the composition of one composed with the inverse, and that's not the 0 element in pi 0 of this diffeomorphism group. Okay, so that's just formal rephrasing of what of my older results. So here's the main step, and I guess I'll just kind of say this and we'll get out. So I'm going to make this Z bigger, and the key insight is that this X, remember I said it was an elliptic surface. So that has an interesting torus, the torus fiber and some vibration with self-intersection 0. So you have to actually pick the right torus. So as I say, the fiber from this E2, and in fact, it doesn't go near that summand of M. So in fact, it's actually invariant under this diffeomorphism. So I'm going to make this a slightly bigger thing. So again, ignore this part. This is now that's gone up to 1. I take what's called the fiber sum. I remove a neighborhood. I take 2 copies of my original Z. I remove a neighborhood of this torus fiber thing, and I glue them along in sort of the obvious way. So here's kind of, a picture. Dave always calls this a cartoon, so I guess that's a cartoon. But this is supposed to be the picture. So I have 2 copies of Z, and in each one, so over here, this corner, that's the M. So I have that's sort of where the 2 spheres sort of live. One of them actually the way I've drawn it, lives in there, and the other wanders elsewhere. We don't quite know where that's gone. But it doesn't hit this torus. And here's another one. I haven't drawn the other copy of the spheres, although they're relevant. And now I just glue them together. So I couldn't artistically draw them glued together, so I sort of flipped one over. Anyway, here, this is the 2 copies of Z glued along a torus, and this is sort of where the torus lived. And sort of there's a one in my picture, there's the one on the left, that's sort of this part, and there's the one on the right, and we're going to use them both. So look, in this right-handed M, there's a CP2, and that's enough to make the sphere SX, sorry, in this part, this sphere SX here and this sphere SY there, those become isotopic in this bigger manifold. Okay, so that says that, in fact, if I do the diffeomorphism, well, okay, it's the diffeomorphism of this piece connects some with the identity on the other piece. So this is the left one and it's the right one. You have to keep it all straight. That's isotopic to the identity on this new manifold. Okay, that's the key. That's really the key observation. And okay, so then we're just going to use that to, so, what's an isotopy? That's a 1-parameter family of diffeomorphisms. And so I'm going to take that, and you have to do a little bit of just kind of elementary fiddling to see that this is a sensible definition. Let me call F the isotopy. So I don't know why I use the notation from the paper. So it's F0 is this isotopy. So that's, as I say, that's kind of the fundamental object, is that thing. And that F gets used over and over and over again to make higher isotopies, so to speak, or families of diffeomorphisms. So I'm going to write it. So I'm going to get a loop, and you have to sort of parse this formula, which I think I will not do in public. You take the commutator, you take F. So F, that F needed the CP2 that was in here, but it leaves alone the CP2 bars. Okay, those are sort of along for the ride. So I can take F, extend it a little bit. So this is a 1-parameter thing, and I take its commutator with this diffeomorphism. So I just think this is really now a function of T, and you just check that at the endpoints, it gives you the identity just because of the way it's set up. And so this is a loop. So if you just sort of, you have to kind of fuss with this in the way that like when you're learning.
Alpha superscript 0?
Alpha 0 was Alpha 0 was this one.
Oh, okay.
Right. And actually, this is the alpha. So sorry, Alpha 0 is this one, but this is the one on the right. Okay. And here we have the F0. Anyway, by the time you're done with when you write out the commutator, because at either end, this is either the identity or something that's just supported completely on the left, they commute. So at t equals 0 and t equals 1, you get the identity. So that's why it's a loop. Okay, so anyway, that's the you get this loop, and if you keep track of the spheres Sx, well, I guess the sphere X as X. In fact, that I have a loop of diffeomorphisms, and well, if I have a sphere, then a loop of diffeomorphisms gives me a loop of spheres. And well, keeping track of the boundary of the tubular neighborhood, that's a loop of 3 spheres.
Can I ask a question? So I think if I remember correctly, Z01 was X connected some CP2 and 2 copies CP2 bars, right?
Yeah, yeah.
But in this notation, in the commutative formula, you had the identity was just on X connected some 2 copies of CP2 bars.
Yeah, so that's because F0 sort of uses it's a little, the notation's not really ideal. I mean, in the paper, we wrote this out sort of maybe more carefully, but in F0 sort of uses up the CP2 because the CP2 is not fixed here. So it's just, you take the rest of it.
Okay.
Yeah. No,
okay,
it's a little bit tricky to write all that out. Anyway, I think the formula, the formula is morally correct, and I may not have written it down entirely properly. Okay, so I guess I didn't leave myself much time to say the rest of the story, but let me just say, so in my old paper, I defined here. Let me just sort of draw this little chart, and so there was a sort of progression of ideas, and so this was, this is really Donaldson's original program. This is for to define what's called Donaldson invariants. And what he said was, well, you solve some equations, and the point is those equations depend on choosing a good Riemannian metric on X, and you count the solutions to some equations up to equivalence. And I left out the technical details, but we arranged that that's somehow a finite set of points with signs, and you can count them with signs, and that gives you what I was referring to, dx. And a similar program, of course, works in other gauge theories, so particularly Sauger-Witten theory. What I did was do a similar idea where you had a diffeomorphism. You pick a metric, you pull it back by this diffeomorphism. That's what this picture is supposed to be. I connect them by a path because, of course, the space of metrics is connected. And then I've arranged it, as it turns out, you arrange it so that what's called the one parameter moduli space, where you take the same equations as parameterized by a path of metrics. So that's, sort of formally adding 1 to the dimension. That would be 0 dimensional. And so you count points there. That's the Donaldson invariant of a single diffeomorphism alpha. And then a similar program, this is what Dave and I did, which again, we were aware of for many years before we worked out how to calculate it. So it, as I say, the idea dates back to whenever I first did the original work, but we didn't have any idea how to calculate it or give examples. So in any case, so same idea, we can get use parameterized gauge theory to cook up invariants of say a sphere's worth of diffeomorphisms. And so the theorem that I guess I quoted before was that in the situation that we're describing, the sort of my original invariant for this alpha 0, that's twice the difference between the Donaldson invariants of the X and Y that we started with. And now here, for the higher parameter ones, we get a similar thing. So the invariance for ZK, ZK, is the invariant for ZK is if I sort of take alpha k minus 1 with all the properties, build myself an alpha k, then you just get the same invariant, well, multiplied by 2. Okay, and so that says that you get non-zero, and so you get a sequence of manifolds, and at each time you make them bigger, and of course these manifolds are getting sort of large in some sense. The homology is growing linearly with k at least, and the point is that, but each time you do that, you get more non-trivial homotopy groups, and well, and then as I say, if you wanted to get higher rank things, you just apply a little more for manifold topology. Okay, so that's you know, and there's a similar. So the recent sort of technical advance, as I was saying, has to do with doing this for instead of doing spheres worth of diffeomorphisms, we have sort of a cycle in the diffeomorphism group, or a cycle in the classifying space. So that's really talking about families of manifolds. But I'm certainly not going to go there now. So thanks for the attention, and I think I just about made it. Okay, thanks.
Thank you very much. Questions from anyone?
I'm not familiar with the Donaldson invariant. So can any of these theorems be proved using the Cyber-Witten invariant?
Oh yeah, so the basic structure works great for the Cyber-Witten invariant, in fact, this theorem or this calculation for higher homotopy groups works just the same if you did this for the Cyber-Witten invariants. But there's a sort of what seems like a minor but aggravating technical point, which is going from the pi0 results to the pi1 results. It's a little bit tricky, and that has to do with the fact that this alpha 0, as constructed, is a composition of two diffeomorphisms, each of which acts non-trivially on homology. And so each of those things, each of those diffeomorphisms moves around the spin C structures. And for that reason, it's a little, the theory behind the everything in dimension 0 is a little trickier. So I don't recommend teaching this to your introduction to proofs class, but this is like one of those classic bits of induction where everything works great, except for you have to do the base case. So anyway, so we're a little stuck on the base case in the Cyber-Witten class. As I say, I don't think I would teach that in my introduction to proofs, but it is exactly that situation.
Would there be any payoff to making it all work Cyber-Witten? Like, could you get more in any chance?
Well, there is a payoff. First off, everybody always asks us about it, so that would be a payoff. But first off, in the Cyber-Witten case, this 2 would be a 1. That would be nice, because that means that we would see, what is this doing? This D is giving a homomorphism, and it's not actually, as it stands, a surjection onto Z to the R. So you get a Z to the R. So you have to replace your Z to the R subgroup by some summand that contains it. So that's sort of irritating. And if you didn't have that 2, then you could actually get you just get a summand right off the bat. And when you replace the subgroup by a summand that contains it, then you lose some of the things like this stably being trivial and the topological. I forget, maybe you lose the topological triviality. So the statements of the theorems would be a little neater. You know, conceptually, it's not really that big a deal. It would have other applications, like you could say something about the space of positive scalar curvature metrics on higher homotopy groups of the space of positive scalar curvature metrics, which was something I did with in the pi0 case, but again with some sort of technical unpleasantness related to this point about moving the spin C structures around. So yeah, and also it would fit in better with this is a fairly active sort of area cooking up invariants of this sort with, I'm sure maybe you've seen this really nice works of Kono and Baraglia and various other people, and mostly they're using the Cyber-Witten equations. We'd like to just see how our things fit together with what they're doing. So yeah, there's a big incentive. We've sort of taken we have a little bit of technical work yet to do in finishing our paper, which we're very frustrated about, but we've kind of taken a vow that we're not going to think about anything new until we actually write down every detail in our paper. So someday there will be Cyber-Gwitten version of this talk, and we'll have certain it has some immediate corollaries, but mainly, as I say, it's for future reference, and for other projects.
So where does the two difference between 2 and 1 in Donaldson and Cyber-Gwitten come
Yeah,
from?
that's a great question, Gordon. The two. So what are these theorems really? This theorem here or this theorem here? What you're really doing is, if you just go back to wherever well, even in the definition of this alpha, or the computation of the invariant for the alpha, basically you have no idea what's going on X, but you have a very good idea of what's going on M. So basically, the path of metrics you use, like in calculating the invariant here, is really all. It's not doing anything on the X piece. It's doing something interesting on this manifold M, and and M has B2 plus equals 1, and the contribution you get from the way the Donaldson invariants of X or Y come in is the contribution you get is when you pass through a reducible. And so you have to describe the local picture of that reducible. And in the end, the way it contributes is you have an obstruction bundle, and the section of that obstruction bundle, the obstruction bundle essentially you identify with the tangent bundle of the two sphere. And that's where the 2 is the Euler class of the two sphere. When you do the same thing in Cyber-Gwitten theory, the obstruction bundle is not the tangent bundle of the two sphere, but the Hopf bundle. So you're getting the Euler class there is 1. So that's the 1 instead of the 2, and that's why that's better. Or that's why I don't know. That's the difference. Yeah. Thanks. That's a good question. Thank you.
Thank you. So that, let's see.
Should we thank Danny one more time, and then we can continue to harass him?
Yeah. I have no. Yeah. Thanks.
Thanks, Danny. Stop recording. Keep them going if you need to.
So the problem that you mentioned about Cyber-Gwitten is because of that the composition of that two refractions along the -1 sphere. Is that correct?
Yeah. Well, it's so the way that this works is it's that sorry, let me see, where did I define it?
Further.
Alpha. So here the alpha is built out of the basic alpha, and the same thing works for all the other ones. The basic one has got this one and this one. Now, this whole diffeomorphism here, because the spheres are homotopic, this guy acts as the identity on homology. So it's no trouble at all to define a Cyber-Gwitten invariant for that, because all the basic, and for any spin C structure we're interested in, it's taken to itself. On the other hand, and now the Donaldson invariant has a little extra freedom in that you don't have to worry so much about spin C structures. All you have to worry about the bundle, all you have to know, like to say that a bundle is taken to itself, all you need to know is that it's W2 is taken to itself. These are actually, as it turns out, these are SO3 bundles. And well, you need to say it's Pontryagin class or its second Chern class are taken to itself, but that's sort of for free because you're talking about a 4-dimensional class and a map and a diffeomorphism. So all you have to do about it is just a mod 2 condition. And in this case, the action on mod 2 homology is trivial. So that means that there's a separate invariant for this one and a separate invariant for this one and a composition law. So really the calculation is the invariant of just of the one piece. And then it's this one. And then there's the composition law says that when you compose things, the invariant adds. And well, so therefore, when you take the inverse, it subtracts. And that's why I got the Donaldson invariant of X minus the Donaldson invariant of Y. And the problem for the Seiberg-Witten invariant is that at least the way we've got it set up, and probably there's some little variation or some clever trick that we're just not thinking of. And as I say, because we're not allowing ourselves to think about it till we finish the damn paper, is that the invariant that so there is an invariant for just this diffeomorphism or just this one, but it doesn't satisfy a composition law. At least, at least in the work so these are old works of mine. And in those older works, the composition law doesn't work the way you want it to work. So that's really the problem in a nutshell. So we might be, maybe we can, fiddle around and find some diffeomorphism that does, some other diffeomorphism to start off with. But that's the whole problem, is that we don't know how to calculate the invariant of this composition anymore, because we can't just do two separate compositions. So in fact, that was sort of back when I was doing this work originally, that was actually for me, the breakthrough was realizing that, because I was looking at this composition and trying to calculate the invariant directly, but that composition is really complicated, because I have this, I have these two spheres. I have Sx and I have Sy, and they meet each other in some number of points. As far as it's either 3 or 5 would be the minimal number. It can't be 1. In any case, they meet each other, and the diffeomorphism is supported, like this composition is sort of supported in a neighborhood of the regular neighborhood of these two spheres. But that's a pretty complicated regular neighborhood, and I don't know how to. Well, I was having a lot of trouble doing computations that way, and in fact, I went into to discuss this with Tom Rufka, and he said, well, are these ones themselves well defined? I said, oh yeah. So do they satisfy a composition law? And I said, yeah. He said, do you know how to calculate the invariant for these? I said, yeah. And he said, well, then you're done. So, which was like, that was after like a year of struggle, and sort of maybe not a year, but a good long struggle to write it down. And so I don't know that same, but that's in the Donaldson case, and I don't know how to do the same principle in the Seiberg-Witten case. So it's a technical issue, and I'm sure it will get sorted out. And we have a number of ideas, but we haven't finished. We haven't allowed ourselves to think about them too much.
Danny, these, you've got a loop, let's say the pi1 case, I guess.
Yeah.
You've got a loop of two spheres in Z11, whatever.
Yep.
That's Z thing is it really just connects some CP2s and CP2 bars. You probably make it S2 cross S2. It's pretty simple manifold, right?
Yeah. Well, they're not spin, so it's not just S2 cross S2. Anyway, but yeah, sure. Yeah, you could certainly, you do have those nice loops. Yeah.
Right. So I mean,
what are they?
Can we draw pictures of them? Can you see them?
In principle, yes. Because as I was pointing out, this isotopy F, this one here that everything is based on, that, so this formula, although it looks kind of messy, isn't really that hard, isn't really that complicated. And that isotopy is really simple. That isotopy comes down to the fact, let's see if I can remember the.
Well, I was going to ask you this for there is sort of you say the isotopy. There's sort of an obvious one.
Oh yeah, well there is an obvious isotopy, and we wrote it down very carefully. It comes down to, actually, if you want, I could change my screen sharing and show you a picture from some notes of Dave's. it comes, it really, it's actually, the whole point is well, maybe you know this. So the reason we were working with this particular pair of manifolds is that that is the exact pair of manifolds that Auckly used to show in the original proof that his original quark is non-trivial. So yeah, and the point is that inside, in fact, I could show you the whole show. This is copied out from Gomp and Stipsich. So give me just a second. I will unshare and then reshare. So let me see if I can, let me see if I can do this. Share screen. Yeah. Is that showing?
Yeah.
Okay, good. All right, so this picture up at the top here this is a picture, not the whole thing. This is, or maybe this is the whole thing. No, I don't. Yeah, this is straight out. I forgot what page in Gomp and Stipsich you can find this picture. This is a picture of the blown up K3 surface. I think the way it's drawn. Yeah, and yeah. So here's the blow up. Is my cursor showing on here?
Yeah.
Okay, it's it's always disconcerting. Okay, then you do some handle slides. It looks like this, and inside of that you see, I think we did some blow ups. You do some blow ups, and inside of this you see this red dotted curve. That's a one handle, and then the blue undotted one with framing 0, which taken out are this bit up here, right? That's a quark. I mean, that's a contractible manifold, and it's easy to see. Although maybe the full decomposition is a little more work, but it's easy to see that if you interchange the dot and the 0, in other words, you do the quark twist, then all of a sudden, well, for instance, like you see in the original picture, you have this thing with a 0. I think that's the one. Maybe that's the one I want. Or, oh, sorry. Yeah. Well, either that one with a 0 or this. Yeah, take that one with a 0. That two handle with a 0. So that's a homology class of self-intersection 0, I think. Or anyway, some positive self-intersection, non-negative self-intersection, and it's because of properties of the blown up K3 surface. It's not represented by a two-sphere. But if you do the quark twist, then all of a sudden it is represented. It's still an unknot, and you just fill it in with a disk here, and then the core of the handle. It's represented by a two-sphere, right?
Yeah.
So that means that you've changed the Donaldson. You've killed the Donaldson invariant. So the first one was X, and the second one was the Y, and in fact.
Can I stop you? So
Yeah.
why was it not represented by a 0?
Well, because the blown up K3 surface has a non-trivial Donaldson or Seiberg-Witten invariant.
Oh,
And in such amount, and B2 plus is positive, so there's no two spheres of self-intersection 0.
right. Yeah, no, but where in this picture it looks like there is.
No, it doesn't, because you see the 2. That means that
It's going
two
over.
handle, it goes over the two. It goes over the two
The
handle.
one handle, right?
Yeah. So we don't see that.
Okay.
Yeah.
I missed the dot there.
Yes. Yeah. And the point is, so if you get rid of that dot, then of course, as you're observing, then you just there it is. It's an unknown. You just fill it.
Mhm.
So that's I mean, I'm not sure. I don't think that's exactly the picture. That's not the picture that Salman drew, but that's kind of the picture that everybody knows, because Gomp and Stipsich wrote it out. They just they cleaned it up, and I mean, I think that's basically Salman's proof. I actually don't remember what all 10 pages of pictures. Any case, so here's a point. So just look at this quark here. If you add, well, I can't remember. What do I want to do? I think maybe I want to just, well, let's do the simpler thing with the S2 cross S2, and then you have to be a little more careful with No, I think that's the point. If you blow up, if you take a CP2 and you blow up once, then you can basically undo then the cork sort of falls apart. And you see that after you add CP2, the cork twist extends. Okay, so that's not so hard. Actually, it's easy if you want S2 cross S2, because that just is equivalent to making this thing into a zero, that dot into a zero. That would be adding S2 cross S2. But you can also just do it with CP2. And so then you have two spheres. What are the two spheres? Well, there's the sort of the core two sphere of the CP2, and then there's its image after you do this extended cork twist. And those guys aren't the same. So here's sort of a picture of them that you can derive from this other one. So one is basically here's this is a surface, and this is a surface that has it's a ribbon knot, as you see, and the ribbon has two distinct ribbons. So the two ribbons are given by these blue ribbon moves. And those things are not isotopic in the 4-ball REL boundary. That's actually not hard to prove just by pi1 computation. But if you add, but this argument says that if you add a handle with framing +1, in other words, now we have two spheres in this manifold. So by the way, so let me just say it again. If I take this knot and add a handle with +1 frame surgery, that's this cork. That's the cork with connect some CP2. Okay. So I take the cork, add CP2, I get this manifold. In other words, and in that manifold, using the two different ribbons, there's two different two spheres, and you have to argue that those two spheres are given by taking one of them, and the other is the image under involution. And you see that just because in that picture, you just sort of the two ribbon moves are interchanged by a symmetry of the knot that moves the Seifert surface. Okay, so those are those two spheres are distinct, and then you just have to. So then we prove in our paper that if you add S2 cross S2, or I think we have to add S2 cross S2, then in fact they become isotopic. So what's easy to prove is that there's a diffeomorphism taking one to the other. It's a little fussier, and we actually wrote our paper is a little fussy on this point because we had to work for it. So we wrote out a rather detailed proof that you actually see an isotopy after adding S2 cross S2s. So again, I don't know if there's any graduate students still hanging around after all this.
Yes.
Yeah. Okay. So a delicate part of this whole business is that to define to actually argue that something is an isotopy, you have to really sort of see all the stages of the isotopy. You can't just draw a couple of pictures and say, well, this one is diffeomorphic to that one, because you actually don't know that the diffeomorph, like if you have a sequence of different pictures of something, that's not necessarily an isotopy. So any case, so it's a little fussy to prove that they're isotopic after one stabilization. So that's it. And the isotopy is pretty straightforward, actually. Basically, you can kind of untangle that ribbon move from the kind of slide the ribbon move over something, and you have to argue that actually gives you an isotopy. So, as I say, most of this I think is familiar. You could just start with this picture right here, which I claim is related to this other picture, but you could just start with this picture. You see the isotopy after you do a single stabilization, and so that's pretty explicit. And then you can see what the diffeomorphisms. So okay, so now you want to see that loop of diffeomorphisms. Well, then you have to put the whole thing back into the big picture and then start dragging those spheres around. So I've never done that. That would be I think, pretty non-trivial thing to do. I mean, you could appreciate in principle how to do it. Like the tools are all there. It's just that like actually carrying it out, I don't know. That sounds hard-ish.
Thanks.
Yeah, if you ask Dave that question, he'd say, "Oh, it's easy. Just do the," he'd start talking. But I